Welcome back to the next video, everybody. So over the course of the last few videos, we have finished proving proposition 1 on our initial cohomology bounds, and we're going to continue pressing on toward the proof of the general case of R equals T by developing something that we're going to call proposition 2. For that, we're going to have to first learn a little bit about type sigma cohomology, and so we're going to start that right now. So let's set the stage. We'll assume that L is an odd prime. We'll let K be a field as before. It's the residue field of our ring O that we've been working with. It'll have characteristic L. And we'll let rho bar from GQ to GL2 of K be a continuous, semi-stable at all primes, absolutely irreducible representation with cyclotomic determinant. So for example, if E over Q is a semi-stable elliptic curve, then rho bar EL, the mod L representation attached to E, satisfies all these conditions as long as it's irreducible, which is the case, for example, if L is a prime larger than 7 by Mazur's isogeny theorem. Okay, so we covered all this in chapter 1 of the playlist. We'll let C sub O denote the category whose objects are complete Noetherian local O algebras with residue field that same field K, and whose morphisms are local O algebra homomorphisms. We'll let sigma be a finite set of primes, and we'll let R be an object in the category C sub O. So, given all this, we'll say that a continuous lift rho from GQ to GL2 of R of rho bar is type sigma or of type sigma if a couple of conditions are satisfied. So first of all, if rho has L-adic cyclotomic determinant, we don't want to lose that. We also want rho to be semi-stable at L. We don't really want to lose semi-stability at that key prime L. And then sigma will sort of govern the rest. So we want to be sort of well-behaved outside sigma. So if L isn't in sigma and rho bar restricted to G sub L is good, then rho restricted to G sub L is good. So we want to lift goodness outside of sigma at L. Because remember, sort of goodness is the thing we want at L, kind of unramified is the notion that matches that most closely away from L. Okay, so speaking of that, if P is a prime that's not L and is outside sigma, and rho bar is unramified at P, then rho better be unramified at P. And then finally, if P is a prime that's not in sigma and isn't L, then we want rho to be inertially unipotent at P, which means we want the image of rho when restricted to I sub P to be inside 1 star 0, 1. Okay. So for example, if E over Q is semi-stable at L and rho bar EL is irreducible and semi-stable, then rho EL is a lifting to Z sub L of type sigma as long as sigma contains the primes of bad reduction for E. We actually covered this, maybe not in this exact language, but in equivalent language back in chapters 1 and 2. I don't remember exactly where, but this is a pretty easy check. Okay. Let's see. So we're going to recall some stuff from chapter 4 now. We'll let X be a G sub Q module. Remember, we have these restriction maps res sub L from H1 of GQX to H1 of G sub LX. We'll let kind of cal L equal the set containing all these big L sub little l, be a family of subgroups. These subgroups L sub little l and H1 G sub L of X. As L runs through all places of Q, we'll have the property that they're unramified classes for all but finitely many L. So big L sub little l should just be H1 of G sub L mod I sub L, comma X to the I sub L. Okay, so this was all covered back in chapter 4. We call this a collection of local conditions. Okay. Another definition from chapter 4 was the generalized Selmer group associated to a collection of local conditions L is H1 sub L of QX. It's written, and it's defined to be just the set of all X and H1 of GQX, so kind of a full cohomology group, that restrict under the res sub L maps down to L sub little l for all little l. Okay. So it's kind of everything up here that restricts down to the right place in all of these different subgroups as L varies. Okay, so let's define H1 sub sigma. Let's define some type sigma cohomology now. Let rho from GQ to GL2 of O mod lambda to the n, remember lambda was our maximal ideal, be a type sigma lifting of rho bar, the rho bar from earlier. We'll define H1 sub sigma of Q at 0 rho to be H1 sub L sub sigma of Q at 0 rho, where now I just really have to tell you what the L sub sigmas are at each prime. Okay, so that I have a collection of local conditions here. So first, if P isn't in sigma and isn't L, then L sub sigma P will just be unramified classes. So it'll be H1 GP mod IP at 0 rho to the IP. If P is in sigma but isn't L, then L sub sigma P will be H1 of GP at 0 rho. So it's kind of everything at P, so to speak. If L isn't in sigma, then L sub sigma little l is H1 FGL at 0 rho. So we're looking at flat classes. And if L is in sigma, then L sub sigma little l is H1SS GL at 0 rho. So we're looking at semi-stable classes. Okay. It's not hard to check that a choice of generator for Hom O mod lambda to the n to QL mod ZL as an O module admits an isomorphism between the first Tate twist add 0 rho of 1 and the dual add 0 rho star, and that the O submodule of H1Q add 0 rho of 1 corresponding to H1L star sub sigma of Q add 0 rho star, kind of under this isomorphism, is independent of that choice of generator. So we're going to denote that submodule just by H1 sub sigma of Q add 0 rho of 1 for kind of obvious reasons. This is kind of the motivation for that notation. Now, this is also defined by a family of local conditions, L perp sigma V. We talked about kind of orthogonality of local conditions back in chapter 4, but I'll just tell you the orthogonality here is with respect to the pairing H1GB add 0 rho cross H1GB add 0 rho of 1 to QL mod ZL. And this pairing arises from the perfect trace pairing that we have on add 0 rho. Okay. So, I mean, more explicitly, like if P isn't L, we talked about this back in chapter 4 also, what explicitly are these subgroups? L perp sigma P, if P isn't in sigma, is just unramified classes. Okay. And then L perp sigma P is just trivial if P is in sigma. Okay. Perfect. So we've got all the groups kind of laid out in front of us for these families of local conditions. So what next? Let rho from GQ to GL2 of O now be a type sigma lift of rho bar. So we're not looking mod lambda to the n, we're looking just GL2 of O. We're going to want to be able to sort of look at type sigma cohomology after tensoring up to K mod O. Okay, so we'll define H1 sub sigma of Q add 0 rho tensor K mod O to be the limit of the H1 sub sigmas of Q add 0 rho tensor lambda to the negative n mod O, and this limit is over n. And we can make an analogous definition with add 0 rho replaced by add 0 rho of 1. So here is proposition 2. It's one of the key propositions when you're trying to prove R equals T in the general case, kind of along with proposition 1. So let's keep all the above notation. Then there exists a categorically universal lifting rho U sub sigma. So we'll call this a universal type sigma lifting GQ to GL2 of R sub sigma. So we'll call this kind of universal deformation ring R sub sigma. This will be a lift of rho bar of type sigma. So not only do like universal deformations exist in general, but universal type sigma deformations exist, is what this proposition is saying. And moreover, they have some properties. So if K prime over K is a finite extension and R prime sub sigma is the corresponding universal deformation ring, how do you relate R prime sub sigma to R sub sigma? R prime sub sigma is just R sub sigma tensor O prime over O. And how do you relate the universal type sigma deformations? Rho U sub sigma prime is just rho U sub sigma tensor 1. Very simple relationship. 2, and this is very important, kind of how big is R sub sigma? R sub sigma can be topologically generated as an O algebra by dim K H1 sub sigma of Q add 0 rho bar elements. So there's a relationship between our cohomology groups of type sigma and our universal deformation rings of type sigma. This is huge. Okay. And then 3, if phi from R sigma surjecting onto O is an O algebra homomorphism, if rho is phi composed rho sub sigma, and if kind of, I don't even know what we want to say here. If this like phi looking symbol is the kernel of phi, we'll call this WP. So if WP is the kernel of phi, then the homomorphisms from WP mod WP squared to K mod O, those are isomorphic actually to H1 sub sigma of Q add 0 rho tensored up to K mod O. So this is telling you that you can interpret like the tangent space of your universal deformation ring cohomologically, okay, which will also be pretty crucial for us. So let's look at the proof of this. We've actually done most of the work back in chapter 8 on deformation theory, but let's give an argument. So let's let K naught be the fixed field of rho bar. Given a natural number n, let K sub n denote the maximal elementary abelian L extension of K sub n minus 1 unramified outside sigma and L. And also the set of primes where rho bar is ramified, we can't be bothered with those. And then we'll let K sub infinity just be the union of all the K sub n's. And we'll let G be the Galois group of K sub infinity mod Q. Okay, unwinding all these definitions and consulting your number theory textbook, this just tells you that any lifting of rho bar of type sigma factors through G. Okay, also this Galois group, where Q has been replaced by K naught, is a pro-L group by construction, and it has a finite maximal elementary abelian quotient, which is actually just G of K1 mod K naught by Hermite-Minkowski, essentially. Okay. So the following routine lemma then will ensure us that this Galois group and G, the full Galois group here, are topologically finitely generated. Okay, so lemma, this is a generic group theory lemma, so I won't prove it. Let H be a pro-L group and let H bar be its maximal elementary abelian quotient. If H1 through Hn and H map to a set of generators of H bar, then H1 through Hn actually topologically generate H. And here's a reference for you of Coke, if you'd like to go read the proof. All right. So we have, thanks to that lemma, that these two guys are topologically finitely generated. Let's continue the main proof now. Let's let D be the category of pro-finite O bracket G modules M such that three things are true. M is semi-stable as an O bracket GL module. So semi-stable at L, basically. We're going to turn a lot of our conditions that we desire about representations into conditions on modules. That's what's going to happen here. If L isn't in sigma and if rho bar is good, M better be good. That's 2. And then 3, if P isn't in sigma and isn't L and rho bar is ramified at P, then there should be an exact sequence of O bracket I sub P modules. So we're looking over the inertia group at P now. 0 to M negative 1 to M to M0 to 0. Or I px trivially on M negative 1 and M0. This is the so-called, this is the inertially unipotent thing from earlier. Okay. So let's finish the proof and the video. From the definitions, we find that a lift rho from GQ to GL2 of, let's say, A of rho bar of type sigma is exactly that, if and only if three things are true. Well, we already know if and only if rho factors through G. Also, we'll need det rho to be epsilon, so we have cyclotomic determinant. And M sub rho, the representation space associated with rho, is in D. I sort of explained that above as I was outlining the conditions, why this happens. Okay. So now I claim once you've set everything up exactly this way, and I will let you go back to chapter 8 to review all of this, that the existence part of proposition 2 and also part A follow from generic chapter 8 results. If you'd like another place to look, other than back in the chapter 8 playlist, you could also see Theorem 2.36 of the Diamond-Taylor notes for existence and lemma 2.38 there for part A, on the existence of type D universal deformations at large. And then just apply the setup here to that more general result. How about parts B and C of proposition 2? Those follow from the cohomological interpretation of universal tangent spaces that we outlined back in chapter 8 as well. That was towards the end of the chapter. In fact, all of this was towards the end of that chapter. If you want another reference, you could check lemmas 2.39 and 2.40 from DDT. Okay, so that is proposition 2. We are going to start pushing our way towards what I'm calling proposition 3 beginning next video. So I'll see you all then, and thanks for watching.